Very powerful technique, right? Combine the resistors using your series and parallel rules. Come up with an equivalent circuit. Find the current, and then work your way backwards. Works very nicely. Let's try this one. So we're going to attempt this very similar circuit. We're starting out with the same circuit. I've added one more resistor. What do you think? See if you can come up with a series or parallel equivalent for this one. One thing is apparent, you have to get quicker at drawing circuits. You will, I guarantee you will get quicker at drawing circuits. What do you think? What two resistors are you going to hit first? You'd have to be able to go through two resistors without hitting a junction in between them, right? Any of those in series? In series? In series means all the current that goes through one has to go through two. All the current that goes through the first one has to go through the second one. Then we know they're in series. So no matter what path the current takes, if it's coming, current comes here and it splits maybe. Some goes through one, some goes through two. And then what happens? It gets here and it either some goes through the 5 and some goes through the 3, or maybe some is coming this way through the 5 and it's joining with what comes through the 2 to go through the 3. The current that comes here, maybe part of it goes that way and part of it comes down through the 4. So there's a junction between any two resistors. Any path that includes two resistors, there's a junction between them. So that the current could be different in every one of these resistors. Probably is different in every one of these resistors. So no two of these are in series with each other. How about parallel? Parallel means the voltage across the two of them would be the same. And because of the way they're hooked up, no two are going to have the same voltage across them, right? As long as there's current through every one of these resistors, there's going to be different voltages at each point. No two of them are in parallel. Because, well, let's so they're both at the same voltage here, right? They're tied together there. And we drop through the 2 ohm resistor and we're at a different voltage here. And we drop through the 1 ohm resistor and we're probably at a different voltage here. And what's the difference between the green and the blue dot? Well, whatever the current is through the 5 ohm resistor. So if this is a whatever 10 volt battery, then this is going to be 10 volts. And maybe this is, I don't know, 8 volts. And this is maybe 6 volts. And then there's current going through the 5 ohm resistor that creates a 2 volt difference over the 5 ohm resistor. I'm just making up numbers now to illustrate something. But you can see that the 1 ohm has a 4 volt difference across it. The 2 ohm has a 2 volt difference across it. And there's not, if you try to include the 5 ohm resistor, that doesn't work either, right? All right, so we just went through some interesting cases where we said the tool that we had for dealing with this, using series and parallel resistors, combining series and parallel resistors into an equivalent resistor, that was a tool we had for dealing with the circuit, and it was pretty powerful, right? We could get through some fairly complex circuits that way, but not this one. We ran out. That tool is no longer useful. We need another tool in our toolbox for solving this circuits that are even more complicated, right? That's what I always tell my wife. Yeah, I can do that job, but I need to buy another tool. So we need another tool in our toolbox. And the tool that we need is Kirchhoff's rules.